The next paper is MP-NeRF Neural Radiance Fields for Dynamic Multiperson Synthesis from Sparse Views. And we have Xinjin Qiao and Howard Young are the authors. I believe this is online again. Okay, great. So please start whenever you're ready.
Okay. Okay, I can start.
Please go ahead.
Hello everyone. I will be presenting our work on MP-NeRF Neural Radiance Fields for Dynamic Multiperson Synthesis from Sparse Views. First, let's review the novel view synthesis for the objects. The novel view synthesis aims to generate a target image corresponding to the target pose. That means giving a set of multi-view source images and the source pose, which is the transformation matrix from camera coordinates to world coordinates. It can also called as the extrinsic parameters and the intrinsic parameters. And then it could generate a novel view synthesis for the object. And the NeRF is the representative work which can produce very compelling novel view synthesis results that are photorealistic, such as the video shows. And in details, this is the framework of the neural radiance field. At the first stage, the learned things representation using MLP network. The input is corresponding 3D spatial coordinates, which is along the ring directions for the pixel coordinates on the images. And for the each 3D spatial coordinates represent an XYZ, and the view angle represents as a phi. We send them into an MLP network, and using the network to output the corresponding color value and the density value for each 3D spatial coordinate. And as a result, it could using the volume rendering end-to-end learning method to generate the target image, which is different from the input image. And then we could use the L2 loss calculated between the target image and the ground truth image. The advantage for the novel view neural radiance field is that we could not use the 3D as the ground truth. We could only use the 2D image captured from the multi-view setting, and then we could training the whole network to generate a frame view synthesis of the 3D things. And we could see that the L2 loss, including the camera pose and the U represents the pixel value on the image. The theta represents the network parameters of the MLP. And then using the target image of the learned image, we could train the network. In a further step, except for the object, this novel view synthesis could also applied in non-rigid motion, such as the person. The neural body method, which use the input only 4 views images as input, and then it could generate a frame view synthesis for the same person with the same clothes. Well, in details, the neural body different from the NeRF is that it applied a SMPL model, which is the parametric model. Not only have the pose information, but also the shape without clothes. The SMPL model as the input into the sparse convolution net, which could output a latent code volume. That means it will generate a latent code on the vertices of the SMPL model. And this process will diffuses the input codes defined on the surface of the nearby 3D space, which could represent the close, which didn't show in the SMPL model. And the next step, which is the same as the NeRF, for any 3D points, the latent code will pass into the MLP network for density and the color regression. Well, for our work aims to produce the multi-person novel view synthesis. The problems of the previous work is that for the ST-NeRF, which still requires numerous views, around 16 views to generate a multi-person novel view synthesis. And another method called the diplomatic cap, which could use the sparse views as the input, but it could only reconstruct mesh without textures. So the aims of our work is the input is only use the sparse multi-view 2D images, and the output is obtain the 3D texture multi-person frame view synthesis. So we propose the MP-NeRF, which could obtain the frame viewpoint rendering of multi-person video from just 4 to 6 sparse views. And the novel view synthesis of the multi-person has a variety of applications, such as the sports broadcasting, for example, the boxing or other soccer games. And it could also be applied in the tennis presence, which will have multiple performers in this scenario. Next, I will show our pipeline of MP-NeRF. In order to obtain the identification of each person among video frame, we needed to estimate each person's 3D position. So we adopt the algorithm on the multi-view method, which could obtain the 2D joint matching among the multi-views. We could say that the different person will represent different color with the 2D joint projections. But if we applied on video resources, we needed to track the same person along the video, so we could get the identification for each person. In a further step, we needed to using a person re-identification network to obtain the temporal tracking for each person. By combining the two processes, we could get an identity-aware multi-person SMPL model. The following will show the multi-person video as the input. And at this stage, we could get the multi-person SMPL, and the different color will represent the same person along the video. Well, in our next branch, we will build the identity-aware the global latent code on the vertices of the multi-person SMPL model. The input is the identity-aware multi-person SMPL I showed before. Then I will send them into a sparse convolutional net to get the identity-aware the global latent codes. After get the global latent code, we will input the position into the MLP network, which is similar to the NeRF, to obtain the color and the density for each 3D points. Well, for each point, we will accumulate the color and the density along the view direction. For each point, we will get the color and the density, but different from the single person. Maybe here will some multiple volume. So we choose a occlusion-aware neural radiance field to get the color and the density in the occlusion occlusion region. In conclusion, our global latent code will integrate the relative location for multi-person in frame and the identity for each person among frames. Secondly, we will represent each person using a separate volume in combination with an affine transformation. Thirdly, we will correlate the color and the density of each point in each volume, and then we combine them to get the final color and the density of the point. At this slide, I will show the dataset. We utilize a multi-view dataset called the MVMP, which capture 4 dynamic human indoor videos via a multi-camera system, which has 8 views. And each camera is calibrated and provides the 640 multiple 360 resolution with 25 frames per second. And the setting here we use is Adam optimizer, and the learning rate starts from the 5e quarter to -4 and decays exponentially to 5e to -5 along the optimization. The training only using the 4 views videos of 300 frames, which typically takes around 200 kilometer iterations to converge, which will cost 14 hours. And here I show the loss functions. For the CR, which is the rendering image, and the CR is a ground truth image from the 8 views of our data set. And for the theta is the density. And the phi represents the global latent code of our multi-person vertices, and the CX means the color volume for the each point. We will show the quantitative comparisons in terms of the PSNR, MSE, and the SSM metrics on training views and the testing views. And our method will have a better result comparing with the neural body on both thin pose and the new pose. And here we could see the qualitative comparisons. The first row represents the ground truth, and the second row is the neural body result. And we could see that at some occlusion regions, our method will have a better reconstruction compared with the neural body. And this is the comparisons on the unseen pose. For the unseen pose, it will not occur in the training dataset, so it will very difficult to reconstruct. So for both neural body and ours, it will cannot generate a very good result, but our method could also generate a roughly reconstruction of the multiple person. And additionally, we will add some published studies, and we show that using the 6 views will get acceptable results, which could also regard as the sparse views. And for the number of training frames, we found that the 300 frames will be the best choice. And this is the visualizations for the 2 methods. And we could see that for some details, our method will provide clearly details. And for some dynamic, it could also generate some dynamic reasonable multi-person. And this is the rendering result for the single person. And for some positions, it will generate some artifacts such as here. And this is the final visualization of the NOVA views for the 1 frame. We rotated the cameras in the 360 degrees. And we could see that we could synthesize NOVA views smoothly in 360 degrees. The training views is only 4 views. We could generate 100 novel views. And in most views, the shapes, pose, and the relative position of multiple people could be described. In conclusion, our method could have a novel approach for dynamic multi-person synthesis from sparse multi-view videos by the identity-aware global latent code and the occlusion-aware multiple volumes. And for the future work, we plan to improve our work to achieve editing in the 3D content. And we also want to add background for the scene. And finally, the generalization of the new actions and the new characters need to be further improved. And that's all. Thank you for your attention.
Thank you very much for the talk. Do we have any questions?
Can I ask a question? Yeah. So can you? All right. So thank you for the talk. If I understand correctly, the disadvantage of using SMPL is that it's very difficult to generalize to some shapes that are less likely to be human. Say, for example, if someone is wearing a long dress, then SMPL doesn't quite represent that kind of shapes. So have you considered to use other representation instead of SMPL? Say, for example, you can use implicit functions and and like PFU, something like that, to represent a human being.
Okay. Thank you for your question. You mean using the SMPL and the advantage for the SMPL? Here, we use the SMPL as a latent code because the human is not transparent. For the NeRF, it could synthesize the 3D scene representation, such as some transparent. So it will sample the 3D points in the whole scenes. But for the human, we only could reconstruct the surfaces of the human. So we use the SMPL vertices as an instruction and using a sparse convolutional net to diffuse the vertices to a more far position, and then using the MLP network to influence the density and the color, which could obtain the clothes and other shapes, which is far from the SMPL.
So have you observed any issue where SMPL doesn't generalize very well when people are wearing strange clothing, like, well, not strange clothing, but special clothing, like a dress or not trousers? Have you observed that the system may suffer from any issues, or is your system okay with that?
For the losing clothes, this is a good question. For the losing clothes, our network, because depends on the SMPL, so it could not have a good performance on the losing clothes. If we want to generate a good multi-view synthesis for the losing clothes, maybe we need to more detailed latent code vertices, such as using some PyFo HD method, which could represent the more details of the clothes, or some closed human model, which will give more geometric guidance for the novel view synthesis.
Thank you.
Okay.
All right. We will move on to the next episode. Let's thank the speaker again.